The Carnot Cycle. Okay, now let's learn about the Carnot Cycle. Actually, Carnot Cycle is an ideal reversible closed thermodynamic cycle in which the working substance goes through the four successive operations of a isothermal expansion to the desired point, adiabatic expansions to the desired point, isothermal compressions, and adiabatic compression back to its initial state. That is Carnot cycle. So as you see in this diagram, in these figures, you see four pictures of a cylinder and piston. Okay, the first one, A, is a process 1, 2, where it is a reversible isothermal expansion. Okay, where at these conditions, the process, the temperature, high temperature is constant. B is a process 2 to 3. That means it is reversible adiabatic expansion, where the temperature at these conditions drop from high temperature to low temperature. So when I say it is a adiabatic expansion, so the assumption that we have to make is this system is isolation. Okay, is isolation system. Uh, C is a process 3 to 4, and it's called as the reversible isothermal compressions, where the piston is compressed the volume inside the cylinder. And number 4 or D is a process 4 to 1 back to initial states, where at these situations it is a reversible adiabatic compressions, where the temperature raise from low temperature to high temperature. Okay, normally Carnot cycle also called as the two isothermal and two adiabatics process. Okay, now we look more on the reverse Carnot cycle. Okay, the Carnot heat engines cycle is totally reversible cycle. Therefore, all the process that comprise it can be reversed, in which case it becomes the Carnot refrigerant cycle. So you see this is a two PV diagram figures. At the left side is the Carnot cycles. At the right side is the diagram of reverse Carnot cycle. Okay, when you look at these two situations, what happened at the left, the heat is come from source hot to low, but in the right side, the heat we provide from low heat or low temperature to high temperature. That therefore, the Carnot reverse cycles also known as a refrigeration cycle. Okay, this is a difference between these Carnot cycles. So let's learn more about the principle of the Carnot. There are two principles that you have to know when we talk about the Carnot. One the efficiency of an irreversible heat engine always less than the efficiency of a reversible ones operating between the same two reservoirs. Okay. Number two, the efficiency of all reversible heat engines operating between the same two reservoirs are the same. This is the principles that you have to know when you want to make the analysis based on the Carnot cycle. So as you see in the figures, this is the principles what I have told you just now. So it have a two resolver. That's mean source and sink. That mean high temperature resolver and low temperature resolver. So if we look at number one, okay, number one, this one, this is irreversible heat engine. This is reverse heat engine, and this is also reverse heat engine. The principle said if the efficiency of the irreversible heat engine, that means the actual process of heat engines, the efficiency must less than the efficiency of reversible when it operating between two source of resolver. So number two and number three is the same because these two and three use the reverse heat engine or reverse Carnot cycle. Okay, so a reversible and irreversible heat engine operating between the same two resolver, the reversible heat engine is then reserved to run as a refrigerant. Okay, this is when the situations at the left side here, this is the actual, and this is the reversible heat engine, and we can known then as the refrigerator. Also, what happened here? Um, the reversible heat engine is reversed to run as a refrigerator. What I said just now. All right. So this is a combinations. If we put combination of heat engine and also the refrigeration or refrigerator, so what the work irreversible minus work reversible. Okay, so for reversible heat engine or refrigerator, we use work, but for irreversible heat engine, we produce the system produce work. Okay, this slide is only want to show what is the principle of the Carnot cycle. The thermodynamics temperature scale. What is the thermodynamic temperature scale? If you look here, is the temperature scale is independent of the properties of the substances that are used to measure temperature. So it is called the thermodynamics temperature scale. Okay, such as this temperature often great convenience in thermodynamics calculation. So the temperature scales we use is in the Kelvin scale, and and these temperatures in the scales are called absolute temperatures. Okay, so the formula that can be used for using the thermodynamic temperature scales, if QH heat at hot resolver minus by Q low for reversible heat engine is equals to temperature high over temperature low. So this is a temperature scale that can be measured or can be used to measure the temperature using or appraising by the heat. Okay, the heat. So just now I told you about the Carnot cycles. So now we go for the Carnot heat engines. Okay. So at any heat engines, the formula, the thermal efficiency for if you want to measure or calculating uh, can be used can use the formula 1 minus QL over QH. But for any or but for Carnot heat engines, the thermal efficiency is 1 minus temperature low over temperature high. So the thermal efficiency of the actual and reversible heat engines operating between the same temperature limits compared as follow. Okay, this is the comparison when you make the analysis. So when the thermal efficiency of the Carnot heat engines is less than thermal efficiency reversible of heat engines, what happen? It can be categorized as the irreversibly heat engine. When the thermal efficiency of the calculation measurement is equals to thermal efficiency of reversibility, it can call as reversibly heat engine. But when the thermal efficiency is greater than thermal reversible heat engine, this is impossible heat engine. Okay, so this information's knowledge you have to know or you have to remember, because when you do the analysis calculations, when you got the result of the output, when you make the comparison with the thermal efficiency of your calculations, then you can categorize which one is your heat engine, irreversible, reversible, or impossible. Okay, let's see sample problems. A Carnot heat engine receives 500 kilojoule of heat per cycle from a high temperature heat resolver at 652 Celsius and rejects heat to a low temperature heat resolver at 30 Celsius. Determine the thermal efficiency of the Carnot engine, the amount of heat rejected to the low temperature heat engine. So this is a diagram for this system. So it have two reservoir, okay, two reservoir at one at temperature 652 and another one sink at 30 Celsius. So this is the Carnot heat engines, okay. So Carnot heat engine produce work net, and from high resolver it have a high heat, and from Carnot heat engine it pull out the heat from the system to the sink surrounding. So using the formula to find the thermal efficiency for this Carnot heat engine, we use 1 minus TL over TH because this problem is wants you to find the thermal efficiency of Carnot engines. So 1 minus TL over TH, we know the value of TL and TH. Okay, TH is 652, TL is 30 Celsius. From there, you have to convert it to the Kelvin units. So you got the answer 67.2%. Okay, this is the thermal efficiency of this Carnot engine. Number two, number B, the amount of heat rejected at low temperature. So at low temperature, it wants you to find QL, heat that rejected from this system. So using the QL over QH is equals to TL over TH. From here, put all together the values that have been given, rearrange the formula, then you will have the heat rejected is 164 kilojoule. Okay, that is how you made the analysis of the Carnot heat engine. Next, we continue to the quality of the energy. Okay, this is just the knowledge, the theoretical knowledge that you have to know. The question, okay, I ask you or I ask myself, how do we increase the thermal efficiency of the Carnot heat engine? How about the actual heat engines? Okay, so when we look at this diagram of two reservoirs at high temperature and low temperature, it seems that when the high temperature at high heat resolver or source is at high value, the thermal efficiency of the Carnot is increased. Higher of the temperature of the thermal energy, the higher its quality. So this is a knowledge that you have to know. If the temperature is increased, so the quality of the energy for Carnot engine is increased. Now we look on the Carnot refrigerator and heat pump. This is the reverse Carnot cycle. Okay, for any refrigerator or heat pump, the performance we can find using COP, coefficients of performance refrigerator, and also coefficient of performance for heat pump. So the equations will become 1 over QH over QL minus 1 for heat pump, 1 over Q 1 minus QL over QH. So simplify, or you in term of the temperature, COP refrigerants reversible is same as the temperature as the formula of COP refrigerant, unless you only change heat to temperature. So for this coefficient of performance of actual and reversible refrigerators, that's mean operating between the same temperature limits compare as follow. So if COP refrigerator is less than COP refrigerator uh, re, reversible, okay. So this is for the calculations. So this is for the theoretical. So it is will become irreversible refrigerator. If COP refrigerator is same as COP refrigerator reversible, so it's called reversible refrigerator. But if it is more than COP refrigerator reversible, we call it as impossible refrigerator. Okay, the COP of the refrigerator or heat pump is the maximum theoretical value for the specified temperature limits. So actual refrigerators of heat pump may approach these values as their design are improved, but they can never reach them. So however you improve the design, but at the end they never reach at the limit. The COPs of both refrigerators and the heat pump decrease as T low or T at low temperature decrease. Okay, so that means it's required more work to absorb heat from low temperature media. That's why, that is reason why it is decreased. Okay, this is the example, sample example, okay, for refrigerator and heat pump. So, an inventor claims to have developed a refrigerator that maintains the refrigerated space of 2 Celsius while operating in a room where the temperature is 25 Celsius and has a COP of 30.5. Is there any truth to his claim? So to know, uh, you have to find the COP of this system. So for COP for the refrigerator, you know the formula is TL over TH minus TL. So you know the value of the temperature at high and low temperature. So put all the values and then you will get COP refrigerator is 11.6, 11.96. So what happened? This claim is false because it's claimed 30.5. COP is 30.5, but when you make the calculations, you only get 11.96. So it is false. Okay. Okay, I continue. This is a sample problem. Maybe you can do it yourself in your room. These are all the practice problems. Okay, you also can do it in your room. Okay. Okay, we go for the conclusion for Carnot cycle. This is only for the Carnot cycles. Okay. Actually, the Carnot cycle is a reversibly cycle that is composed of four reversibly processes. Two isothermal and another two is adiabatics. Carnot's principles state that the thermal efficiency of all reversible heat engines operating between the same two reservoirs are the same, and that not heat engine is more efficient than a reversible one operating between the same two reservoirs. These actually statements form the basic for establishing the thermodynamics temperature scale related to the heat transfer between a reversible device and high and low temperature reservoir by the formula QH over QL reversible is equals to temperature TH over TL. A heat engine that operates on the reversible Carnot cycle is called heat Carnot heat engines. The thermal efficiency of the Carnot heat engines, as well as all other reversible heat engine, is given by the formula thermal efficiency reversible is equals to 1 minus TL over TH. So this is the maximum efficiency a heat engine operation between two reservoirs at temperature TH and TL can have. So this is in between, okay? High temperature and low temperature. The COP of reversible refrigerators and also heat pumps are given as a similar manner. That means similar. COP are refrigerator reversible is equals to 1 over TH over TL minus 1. And same as a heat pump, the formula is the same. Only you have to twist, okay? You have to twist the formula that is the COP for heat pump reversible is 1 over 1 minus TL over TH. Again, these are the highest COPs a refrigerator or a heat pump operating between the temperature limits of temperature higher and temperature can have. Okay, uh, that's for Carnot cycle.